The continuation of this structure pop quiz 14. So we have to complete a graph for the activation energy. When there's a catalyst is used, the activation energy was 70. And when there's no catalyst is used, the activation energy is 290. So you can select a scale. It's not like you start with the origin because you don't know what energy the reactant have, but you know the energy needed from reactant till the start should be 70 when there's a catalyst, and when there's no catalyst, it should be 290. So if I say take this as the any value, so this will be 50, this will be 100, this will be 150, 200, 250, and then 300. So when we have the catalyst, the energy was only 70, so 50. Here between 0 and 50, 10 boxes, so each is representing 5. So this will be 55, 60, 65, 70. So from reactant till the start of a reaction and it will form a product if the activation energy was 70 and this is with catalyst. But if we were have without a catalyst, it was this is 260, 270, 280, 290. So without a catalyst, the activation energy will be higher. So this is the activation energy without a catalyst, which is an activation energy is always positive, so it's always pointing up. So this is 290 and this one is 70. Is it clear? That's how you have to label. So it's not like the energy of the reactant is zero. It's like from reactant, how much energy we need, that we call activation energy, minimum possible energy, which we need to start up a reaction. The next we have suggests why the use of a catalyst makes stage 2 more sustainable. So it's related to the sustainability of a reaction. So like the sustainability of a reaction refers to how much energy you consume. Because when we use a catalyst, the same reaction can be carried out at a low temperature, and which it reduces the cost, which it reduces the consumption of energy, so make it more sustainable. So whenever you refer a sustainability of the reaction, what you should answer, always refer in terms of the energy and the fuel. So when we use a catalyst, the same reaction can work at a lower temperature because the purpose of the catalyst is to speed up a reaction. And speed up a reaction, we normally use temperature. But if without increasing temperature too much, we can use a catalyst which reduces the cost for production of energy. As a result, uses less energy. So the reaction will be more sustainable. Part E, any doubt? E1, give one reason why a high temperature is needed in this reaction. Usually, as you can see, the forward reaction is exothermic. So if the forward reaction is exothermic, it prefer a low temperature. So reaction prefer a low temperature, but why we are carrying out at a high temperature? So then it is refers to inertness of the reactant, or you can also refers to, so you can mention inertness of the reactant, or you can also mention the activation energy. Like the reactants are inert, or you can say the activation energy is very high. That's why we need, even though the reaction is exothermic, so we prefer that the temperature should be low. But we have a constraint that we cannot have a low temperature. We have to use a high temperature. So why we have to use a high temperature? So because the reactants might have a very high activation energy, or the inertness of the reactant, to overcome the inertness of the reactant, we have to increase the temperature. So always refer this thing when you see why a reaction need a high temperature, so it's two reasons. One is the inertness you can compare, or another one you can mention, refer the activation energy. Part F, any doubts? NO from the first reaction, stage 3, is cooled and then converted into nitrogen dioxide by reacting with more oxygen. Nitric acid is produced by addition of a water. Explain how adding a water for the second reaction affects the yield of nitrogen dioxide in the first one. Look, the second reaction we are adding water, so nitrogen dioxide is reacting with water to form a nitric acid. So as a result, what will happen? Amount of a nitrogen dioxide will decrease, because that nitrogen dioxide which is released in the first stage, it is reacting with the water to form nitric acid. So if amount of nitrogen dioxide will decrease, so as a result, where the equilibrium will shift for the first reaction, the equilibrium will shift towards the right hand side. So how adding water in the second reaction affect the yield in the first? So the yield will increase. Why yield will increase? Because water reacted with nitrogen dioxide, so which reduces the amount of nitrogen dioxide in equilibrium. As a result, the balance will shift toward the right hand side. So the yield of nitrogen dioxide will increase. Part G, any doubt? In part G, complete the enthalpy cycle is there. The data is given, that is when nitric acid from liquid nitric acid from aqueous, it is minus 32, and when ammonium nitrate solid dissolve, it is plus 25.6. And the enthalpy change of formations are given here. So we just have to write these values when ammonium nitrate become aqueous. So this is plus 25.6. So we'll write plus 25.6 here. And the second one is written minus 32. This is the case, minus 32.6 is written here. When nitric acid liquid, when nitric acid HNO3 liquid is there, ammonia is still there, plus nitric acid liquid turn into nitric acid aqueous. And here this is a formation of ammonium nitrate. When nitrogen, hydrogen and oxygen combine, it will form ammonium nitrate. So what is the formation of ammonium nitrate? The formation of ammonium nitrate is minus 365. So negative 365 kilojoule per mole. It's a formation of ammonium nitrate that is given to us. Now what we have to do, the second part, we need the enthalpy change of a reaction. So we need this thing. First, whenever you see a Hess law, how you know where to start? Where the two arrows are pointing out, that is always the start of the cycle. So where the two arrows are pointing out, this is a position where the two arrows are pointing out, that's the start of the cycle. And where the two arrows are pointing in, that is the end of the cycle. So this is the end of cycle. If I follow route 1, if we follow route 1 or we follow route 2, the overall energy change is independent of the path of the route we follow. So the overall energy change does not depend on how it is done. So it is irrespective of the path or the route we follow. So we just write the numbers here, minus 220.2, then plus, then because addition is there, and this is sign is negative, so minus 32.6 plus the enthalpy change of a reaction equals to the root 2, which is minus 365 plus 25.6. Now we just have to simplify this for enthalpy change of a reaction. So enthalpy change of a reaction will be minus 365 plus 25.6 And this is negative, so other side will be positive, so plus 220.2, and plus minus is minus, so it will be minus here, other side it will be added, so 32.6. You just have to simplify. What's the final answer here? The enthalpy change of this reaction. Sum them and subtract it from 365. So minus 87.2. Okay. So negative 87.2 kilojoule per mole is the enthalpy change of this reaction. Part H, any doubt? Suggest two reasons why it is important, more profitable to carry out all four stages at the same site when we are manufacturing ammonium nitrate. So it's related to the cost as well, like transportation costs will be prevented, make it cheaper if it is done at a one site. Question 3, part A. Any doubt? 3B. Part H, they're saying that why this reaction should be done at one site only. Why not? Why separate site should not be used? So if we are doing all at one site, first thing it will reduces the transportation cost. Like example, first you manufacture ammonia, then you reacted ammonia with another site with oxygen to form nitrogen oxide, then nitrogen oxide transported to another place to react and form nitric acid. So why all four stages in the same site should be done? So that it reduces the cost of transportation, and as well as the energy cost and the raw material cost will be reduced. Plus the workforce, the amount of land which is needed, that will also be reduced. Is it clear, the part H? So in question 3b, an experiment is carried out to calculate the enthalpy change of a neutralization for a reaction between sodium hydroxide and sulfuric acid. 100 cm cube of 1 mole per dm cube sodium hydroxide is added to 75 cm cube of 1 mole per dm cube sulfuric acid. The ratio between them. So the ratio between them, when we work out, we need the amount of the moles neutralized. Equation, as you can see, the equation between sodium hydroxide, its ratio is 2:1. So 2 moles are giving 1 mole. So concentration and the results of experiments are shown. The initial temperature of a sodium hydroxide. Initial temperature of sodium hydroxide was 20 and sulfuric acid, but the temperature of the mixture is 27.8. And use calculate neutralize in this experiment. So first find the moles of sodium hydroxide. Yeah, 0.05 will be the answer. Just use the ratio, moles is concentration into volume, and then it will be half of it will be, as 2:1 is the ratio between them. You have like 0.1. This is 0.1, this will be x, so cross multiply. So 0.05 will be the answer here. That will give us the moles of sulfuric acid which are neutralized. Now, enthalpy change of a neutralization using a table and include the unit in your answer. The specific heat capacity is given to you. 1 cm cube of a final solution is 1 gram. There is no heat loss to surrounding. Sulfuric acid fully dissociate, and the experiment is taking place at a constant pressure. So if we need the enthalpy change is energy divided by mole. When two reactants are there, we always use the moles of the limiting factor or the limiting reagent. So this is always the case whenever you need You need a moles of limiting factor, because as you can see, which one is a limiting factor when the sulfuric acid and sodium hydroxide? Yeah, answer the unit. I will tell the unit as well. I will solve in sequence and then I'll tell the unit. So as you can see, we have like a when it's complete reaction, so 0.075 moles are there, because this is 75 cm cube. So 75 will be divided by 1000. And when we work out the moles of this one, so this was 0.1 mole. As a ratio between them, between the sodium hydroxide and a sulfuric acid, we work out like 0.05 moles of sulfuric acid were reacted. But originally we were having a 0.075. What it shows that sulfuric acid is a access reagent and sodium hydroxide is a limiting factor. So this H2SO4 is as an access, more than enough what we need, and sodium hydroxide is a limiting reagent. And if we need the enthalpy change is energy divided by mole. And E is equals to Cm delta T, and the mole we'll use for a limiting factor. So what is a limiting reagent? Sodium hydroxide is a limiting reagent. So we'll use the total moles of sodium hydroxide. How we know the limiting reagent? As you already worked out here, in this part you worked out that the moles of sulfuric acid which will be neutralized 0.05. But originally with this concentration and the volume, there are 0.075 moles. So you have more than what is needed. You neutralize only 0.05, but you have more than what you need. That is, you need only 0.05, but you have 0.075. So sulfuric acid is an access reagent, means a reagent which is more than enough. So sodium hydroxide is a limiting factor. That's the first thing. So we need the enthalpy change, which is the energy divided by mole. So if we need the energy, that is Cm delta T, where C is a specific heat. What is the specific heat? It's given 4.18. So we use that 4.18. What about the mass of the solution? Because the acid is mixed with an alkali. So what is the total volume of solution? 100 was mixed with 75. So if 100 is mixed with 75, the total volume of the solution will be 175 cm cube. And the total volume of the solution is always same as the total mass of the solution, because we assume that the density is 1 gram per centimeter cube. So what about the mass of the solution? The mass of the solution will be same as 175. The temperature changed. Initially it was at 20, the two, and then when we mix them together, the temperature rises to 27.8. So we'll take a temperature difference 27.8 minus 20, so which will be 7.8. So when you multiply this, E is equals to Cm delta T, what you will get the answer? This, you will get the answer in joules. This answer is in joules, because specific heat is there, mass is there, temperature change. What is this answer? 175 times 4.18 times 7.8. So when you multiply this, this is coming out to be 5,678. Okay. 5,678 joules. That is, but we need the enthalpy change. You can convert this into kilojoule, because usually the enthalpy change, the enthalpy change, the SI unit is kilojoule per mole. That's the standard unit. So if it is in joule, you can convert into kilojoule. You divide by 1000. So when you divide by 1000, it will become 5.678 kilojoule. Now we need the enthalpy. So if we need the enthalpy of the solution, it is energy divided by mole. The energy is like 5.678 kilojoule, and divided by mole is 0.1. So when you divide, you will get 56.7 kilojoule per mole. So the method is what is important, that how you work out the enthalpy change of a solution when acid is reacted with an alkali. So always substitute the moles of a limiting reagent when you mix the two solutions, acid with an alkali or a salt solution is added to another salt solution. So always use the limiting factor as a mole. Part C, any doubt? That's the last one. Complete the equation for a reaction that occur when a solution of a barium hydroxide is added to a sulfuric acid and include the state symbol. So when a barium is reacted with barium ion is there and sulfate ion is there, so it will always form a barium sulfate. And that is the solid, the PPT is there. And this is the acid, here is an acid and this is an alkali. When acid react with an alkali, the product will be salt plus water. So water is H2O. What about which salt it will produce? Sulfuric acid produce sulfate salt, so it will form barium sulfate. Then equation, we have to balance the equation. For balancing of this equation, we start with oxygen, followed by hydrogen, and then any other element of your choice you can select. So here you have 4 plus 2, 6 oxygen. Here you have 2. You have to make it 6. So now it's 6 oxygen. State symbol I will write. I did not write the state. I'm balancing the equation first. The oxygen is balanced. Then what about hydrogen? We have 2 hydrogen here and we have a 4 hydrogen. So hydrogen is not balanced. So we have to put 2. So the hydrogen is balanced. But when we balance the hydrogen, now oxygen is not balanced again. As you can see, the balance, the oxygen number is now it's not balanced. And hydrogen, sorry, I did not count there. It's already 4. So this 2 here, I forgot that. This 2 is here and this 2, 4. So hydrogen is already balanced. Sorry. So hydrogen is balanced because this 2 is with here and this 2 hydrogen. So 4 and this 2 multiplied by 2, 4 hydrogen. So this is balanced. Barium is 1 and 1, so it's balanced. And sulfur is also 1 and 1, it's balanced. What about state symbol? Most sulfates are soluble except barium, calcium and lead. So this is solid and water is a liquid. Suggests why enthalpy change of a neutralization cannot be determined using the addition of a dilute sulfuric acid to a barium hydroxide. So what will happen? Why we in this case, like when we were adding sulfuric acid, the last reaction when sodium hydroxide was added to barium sulfuric acid, we were able to determine the enthalpy change of a neutralization. But now we are not able to when it's a barium hydroxide is there and it is reacted with sulfuric acid. So it will form barium sulfate plus water. So why this cannot be determined directly? Because what will happen when you mix a solution of a barium hydroxide with sulfuric acid, it will form a precipitate, a solid will be formed. And this solid precipitate which is formed will absorb the energy because this solid will also absorb energy. So as a result, what will happen? The enthalpy change of a solution will not be accurate. Because when sodium hydroxide react with sulfuric acid, it was forming sodium sulfate. It was forming sodium sulfate plus water. So this sodium sulfate was aqueous, but barium sulfate is solid. So as a result, when the solid is formed, this solid or a PPT will absorb the energy. As a result, the enthalpy change of solution will not be accurate. So we cannot determine directly. Indirect methods are there using the Hess law cycle, but not the direct method. So we want the substance to be aqueous when we are determining the enthalpy change.